Hello and welcome to another podcast episode. My name is Lloyd and you are listening to Starting Out with Quantum Computing. So this week we have a very interesting talk and it's about how do we interpret our quantum reality with cats. So there are many interpretations to quantum mechanics. Some are more popular than others. Let's take a look at what they propose. So quantum mechanics is an incredible theory of reality based on the smallest interactions in the universe. It was first introduced by the physicist Max Planck in 1900, who showed that energy is quantized. And then the theory was made comprehensive by physicists such as Erwin Schrödinger, who developed the description of a quantum system evolving in time. But admittedly, Schrödinger is better known for his famous cat analogy, which describes superposition. This is where the cat is both dead and alive at the same time within a box. There are, of course, many other famous physicists to mention who have contributed greatly to the development of quantum theory, such as Niels Bohr and Richard Feynman. There's so many. There are, of course, many other famous physicists to mention who have contributed greatly to the development of quantum theory. Although it would be remiss not to outline their work, we will only be able to look at a few. Throughout schools and universities, quantum mechanics is generally taught the same way. Throughout almost a century of trials and testing the theory, quantum mechanics has held up against precise and rigorous experiments, in both the physical and thought sense of the word experiment. But there lies a fundamental issue. Even though the maths and the physics works, what do the answers actually mean for our reality? For example, are the results of quantum mechanics actually real? What minimum amount of observation is required for measurement? Is quantum mechanics deterministic, stochastic, local, or non-local? In most textbooks, for example, the Copenhagen interpretation is taught. And this can be considered the most popular way of interpreting our quantum reality. Although a century of debate has yielded no consensus among philosophers and physicists and mathematicians, let's muse over some of the top interpretations. So, the Copenhagen interpretation. It's one of the oldest and has certainly the most commonly taught sort of method. It's definitely the most commonly taught interpretation. And we can attribute it to Niels Bohr and Werner Heisenberg for first sort of bringing it into the public spotlight in the 1920s, in 1920 specifically. It essentially rests upon the principle that quantum mechanics is intrinsically indeterministic. So, for example, a quantum particle in superposition does not exist in one particular state or another, but in a separate state that represents all possible states at once. It is only when we go to observe said particle that it is forced to become a definite state. But this is a probabilistic process. For example, Schrödinger's cat may be forced into the state of being alive or the state of death upon observation, with the specific probability characterizing the superposition in the first place. So it's not always guaranteed when I observe the cat that it will be dead or alive. It might be a 50-50 chance. Depends on the specific superposition. We call this process wave function collapse. Here, wave function refers to the entire state of a quantum particle system. Basically, how can we mathematically describe the entire thing? And collapsing this wave function means that we force it to take on a definite property rather than to stay in a clouded superposition. Funnily enough, it is said that Heisenberg and Bohr disagreed over what the actual observer is within this framework. However, in their defense, this might be one of the hardest things to actually conceptualize in quantum mechanics. Another interesting thing to emerge from the Copenhagen interpretation is the principle of complementarity. This foundational idea encompasses two main things. Number one, the uncertainty principle, which is taught generally at the start of undergraduate physics degrees. Certain pairs of physical properties cannot be simultaneously ascertained with 100% precision. So, for example, you cannot learn with certainty both the momentum and the position of any particle at the same time. In other words, the more accurately you measure the momentum, the less accurately you can measure the position, and vice versa. Then the second concept within principle of complementarity is the wave-particle duality theorem. So fundamental particles, such as photons or electrons, can exhibit both particle and wave-like properties. This contradiction, which can be experimentally verified quite easily, portrays the limitations of classical theories in describing quantum objects. Now let's move on to a new interpretation, the many worlds interpretation. This is one of my favorite interpretations, and it's very popular. The American physicist Hugh Everett introduced this idea in 1955 whilst being a PhD student at Princeton. His original analogy was the idea that when a cell splits into two daughter cells, each would be identical up until the point of splitting, and then they would have separate memories. Now let's see how this translates to the quantum side. The most important part of this interpretation is that there is no wave function collapse when an observer measures the quantum state. Instead, there is a universal wave function, and all possible outcomes of a quantum measurement are physically realized in different universes. So, for example, in the case of Schrödinger's cat, the alive cat and the dead cat are in different branches of the multiverse. Both exist, but cannot interact with each other, as they are in a different universe. So Everett did point out that since no observer would ever be aware of the existence of the other worlds, to claim that they cannot be there because we cannot see them is no more valid than claiming that the Earth cannot be orbiting around the Sun because we cannot feel the movement. With help from David Deutsch, who is a British physicist from the University of Oxford and is known colloquially as the father of quantum computing, we can take this concept of many universes further. A normal classical computer works on the basis of tiny switches, which are either in the state 1 or 0. A quantum computer, on the other hand, can place the switches into superpositions, allowing for states which are both 0 and 1. Properties such as this can allow for exponentially faster and more powerful computing. Deutsch, therefore, cleverly argues that quantum computer calculations are actually being carried out on identical computers but within different parallel universes, and the number of parallel universe quantum computers is equivalent to the number of possible states within the superposition. This might seem far-fetched, to be fair. You may or may not believe this. It can have some wild implications. For example, a quantum computer with over 300 qubits, which definitely exists now, IBM, Google, etc., have easily surpassed over 1,000. But just a quantum computer with 300 qubits would generate more parallel universes than there are atoms in the known universe. So it is quite hard to fathom the sort of infinite implications of this theory and this interpretation. Now let's talk about the final one. It's quite radical. It's QBism, quantum Bayesianism. This is quite a radical interpretation, and it's radical because it emphasizes the role of the observer and of human involvement. Classical physics generally tries to push an objective viewpoint, the narrative that the universe is made of laws that objectively apply, regardless of whether conscious humans exist or not. QBism is different. According to QBism, the result that outputs from a measurement on a quantum state is merely the observer updating their beliefs after making a measurement. I suppose passively, in a sense. Even entanglement over huge distances is explained using the same logic. QBism treats the wave function of a quantum system as the single observer's subjective knowledge, meaning that one observer cannot affect the observation of another observer, at least within this framework. Personally, I think it's a theory that is unlikely to have much practical significance. It raises a lot of questions, such as how does the observer have to be a human? Could it instead be a dog? Perhaps a flower? So what is the definition of consciousness anyway? How small should the observer have to be? And why can't subjective observations mess with each other? If quantum mechanics only describes the subjective observer's reality, which observer is it describing? If you ask me, these questions will probably be pondered forever. But it doesn't mean that they're a bad thing. To conclude, there are so many fascinating interpretations of quantum mechanics, and I've only been able to scratch the surface on them. I should like to write more about them, and to create more podcasts about them. So please stay posted for another article and podcast in the future. As far as quantum computing is concerned, the interpretation of quantum mechanics doesn't matter so much. The field of quantum computing is more about getting results from inherently quantum systems and thus being able to surpass classical computing approaches. However, in order to design novel quantum computing setups and novel quantum computing algorithms, out-of-the-box perspectives to quantum mechanics may be necessary. Therefore, it is never quite right to completely dismiss a school of thought when it comes to quantum mechanics. Thank you very much for listening to Starting Out with Quantum Computing. My name is Lloyd. If you've enjoyed this week's podcast, please stay tuned for more, and please share with a friend who you think might be interested. Thank you very much, and catch you next week. Bye-bye.